Now that we've kind of mastered all the content we need to master for trigonometry, we're going to move into a slightly different topic as we prepare our transition off to calculus from this course of Pre-Calc 2. The question we're going to take a look at is how can we use trig to graph functions. And the answer to that question is we're going to use something that is called polar coordinates. And with polar coordinates, it's going to be a little different than the way we used to do points. What we've done so far is what are called Cartesian. That might be spelled wrong. But Cartesian coordinates had an x and a y. We've seen those before. And the x would tell us how far to move to the right, and the y would tell us how far to move up. And if they were negative, we would just move backwards. Polar coordinates also have two numbers, but this time the first number is going to represent a radius, and the second number is going to represent an angle, theta. How this is going to work in polar coordinates, and I erased the Cartesian because I don't want that to throw us off, is we're going to have a center grid like before, where we go off 1, 2, 3, 4 to the right, 1, 2, 3, 4 up, and then the negative direction, 1, 2, 3, 4, and 1, 2, 3, 4. But instead of thinking about this as a rectangle where you go right and up, now instead these are actually going to be circles of radius 1 and a circle of radius 2 and a circle of radius 3. It's a really bad circle of radius 3, but you get the idea. And a circle of radius 4, and so on. So these are circles going out from the origin. And the only axis that really matters is the axis off to the right that's going to represent 0. And so we could graph a point. Let's graph point A at 1, pi over 3. Well, 1 is going to be the radius, so I know it's going to go out to the circle of radius 1. Pi over 3 is the angle. So I could almost put in, we've got a pi over 4. There's the pi over 3 and the pi over 6. And we've got all of our angles on here that we're used to seeing on the unit circle. And so this angle here of pi over 3, we're going to draw a line of radius 1, and that gets us to our point. Point A has a radius of 1 and an angle of pi over 3 that it opens up to. Let's try and graph another point. Let's graph the point B, -2, pi over 4. So we did the first one in blue. Let's do the second one in green. When we do pi over 4, we know pi over 4 is this line in the first quadrant, but this time the radius is going to be negative. The negative radius then is going to come backwards out of the origin, down the line backwards 2, and then we get the point B backwards 2 from an angle of pi over 4. Let's graph the point C at 3, pi over 6. And let's graph this one in red. This one's going to have a radius of 3, so it's going to go out to the third circle. But the angle it's going to open up is pi over 6. And so pi over 6 is backwards pi over 6 on the radius of 3. That's going to be my point C. And so you can see we can have positive angles and positive radiuses, a positive angle and a negative radius, a negative angle and a positive radius. We can even make them both negative and kind of combine both together. Let's graph negative. Let's go -4 this time and -3 pi over 4. And I'm going to graph this one in purple. -4 means the radius is going to be backwards 4 from an angle of -3 pi over 4. So there's 1, 2, -3 pi over 4. I shouldn't shouldn't actually label that with a dot because that's not my point. But my angle comes around to negative 3 pi over 4. And then from there, my radius is going to come out negative 4 the opposite direction. And point D actually ends up out here. And so that's kind of how polar coordinates work. We're going to open up by an angle, and then we're going to go down a radius. Because in polar coordinates, everything's a circle, not a square like the Cartesian that we're used to. Now, there is a relationship between the square and the circle graphing systems. Let's look at how we can convert between rectangular and polar coordinates. And the way we're going to set this up is we're going to think about what we know about a circle. This is only the top right side of the circle. And an angle that gets made on that circle with a radius of theta leads to a point x comma y, where x is the distance to the right, y is the distance up. And then the radius that we keep talking about, that's going to be how far it travels down that angle of theta. Well, if I look at that, we can see if I took the cosine of the angle theta, that would be the adjacent x over the hypotenuse of r, which gives us the conversion multiplying both sides by r. R cosine of theta is equal to x. And that gives us a way to find the equivalent x coordinate from a polar coordinate. Similarly, we can say, well, the sine of theta is equal to y over r, the opposite over the hypotenuse. And multiplying by r tells us that r sine theta is equal to the y coordinate. We could also take the tangent of theta is equal to the ratio of the sides. Tangent would be y over x, the opposite over the adjacent. And the other relationship that we know we can use is the Pythagorean identity that x squared plus y squared will equal r squared. These four relationships can be used in different ways to make conversions between what we're familiar with in the past, rectangular graphing, to what we're working on today, polar graphing. So let's look at what that looks like with the point 5, 5 pi over 6 in polar. And we're going to convert to rectangular. So in polar coordinates, since this is polar coordinates, I know 5 is the radius and 5 pi over 6 is the angle. If I want to get kind of a visual of what we're talking about, I can graph that. 5 pi over 6 is back here, and let's say that's a radius of 5. So my point is back here. What's nice that we know on the unit circle, at least, at 5 pi over 6, it's a long distance and a short distance. That's going to help us find the actual x and y coordinates. We know that x is equal to the radius, which is 5, times the cosine of the angle 5 pi over 6. Well, cosine of 5 pi over 6, the x-coordinate, that's a long distance, so it's root 3 over 2. And so the x-coordinate, oh, it's also backwards, so it's negative. That makes the x-coordinate negative 5 root 3 over 2. If I want the y-coordinate, y is equal to the radius of 5 times the sine of the angle 5 pi over 6. Well, we know the sine of 5 pi over 6. The y-coordinate, it's a short distance up, must be 1/2. So the y-coordinate is 5/2. So my final answer, 5 comma 5 pi over 6 in polar, is exactly in the same place as negative 5 root 3 over 2, comma, oops, I should say 5 halves, comma 5 halves in rectangular. And I might even put a little r on this so I know it's rectangular, and I'll put a p on the other one so I know it's polar. Those 2 points are exactly the same point. Let's do another one, though, where we can go the opposite direction. Let's say we've got negative 3 comma negative 3 root 3 in rectangular. And we're going to convert to polar. Get us some room to work here. In rectangular means that's an x comma y. So we need to find the angle, and we need to find the radius. One thing that's going to help me, though, is to draw a picture so I get a visual of where this is. It's negative 3, so it's to the left. Negative 3 root 3, it's down here somewhere. So we would estimate our angle's got to be more than pi. And the radius is, well, we'll figure that out. So what I'd first use is the Pythagorean identity to find the radius. The radius squared is equal to x squared plus y squared, which means the radius squared is equal to, in this case, 9 plus 9 times 3 after I square, or 9 plus 27, 36. Take the square root of both sides to find that the radius here actually is equal to 6. So I've got a radius of 6. Then to find the angle, I would use the tangent relationship. The tangent of theta is equal to negative y over x, so negative 3 root 3 over negative 3, which reduces to positive square root of 3. Well, tangent is y over x. And so I might think, OK, with square root of 3, it's either going to be pi over 3 or pi over 6, because I know those are where the root 3 comes from. Pi over 3, that's a 1/2 comma root 3 over 2, because it's short to the right, long up. Pi over 6 is root 3 over 2 comma 1/2, because it's long and then up the short distance. Which one gives me a tangent that's the square root of 3? Well, tangent takes y and divides it by x. If I use the pi over 6, that would be 1 divided by the square root of 3, which is not what I have. But if I use the pi over 3, when I do y over x, that's going to be root 3 over 1, which is root 3. So that makes me think we're dealing with an angle of pi over 3. Sort of. Notice all this plane I've been doing is in quadrant 1. If you recall from our conversation about tangent, tangent focuses on the right side. And we're not on the right side. We're on the left side. So we have to do a little bit of work to think, OK, if that's pi over 3, what's going to be the similar angle down below? If I can get the right pencil, sorry. That's going to correspond with pi over 3. Well, that's going to be 4 pi over 3, which has coordinates of negative 1/2 comma negative root 3 over 2. And when I divide those, I'll get a positive root 3. So my angle theta must be 4 pi over 3. So obviously, knowing our unit circle and relationships is going to be very helpful as we find the correct points. Drawing a picture will help a lot. 6 is the radius, and 4 pi over 3 is the angle. And that is the exact same point in polar as the rectangular point, -3, -3 root 3. We can make these conversions with points, but we can also make these conversions with equations. Let's try an equation real quick. Number 4, equations. Let's first do equations where we take a polar equation and convert it to a rectangular equation. Let's start simple. Let's start with an equation r equals 2. What we're going to try and do to convert this polar equation to a rectangular equation is we're going to try and manipulate it so that it looks like, or at least a piece of it, looks like one of our formulas to convert between polar and rectangular. And while we don't have an r equals equation, we do have an r squared equation in polar. So to make r into r squared, I can square both sides of this equation. And that's going to give me that r squared equals 4. And what's nice is we have a conversion for r squared. R squared is equal to x squared plus y squared, which is still equal to 4. And now I've changed it to a rectangular equation. Let's try another one. Let's do r equals 5 cosine theta. Here we could square both sides again and get r squared, which we know we can replace with x squared plus y squared. The problem is if we square the right side, then we get 25 cosine squared, and that doesn't convert really well with our formulas. But we can do something similar. What if I multiplied both sides by r? If I multiply both sides by r, I get the r squared on one side and 5r cosine theta on the other side. And this is nice because when we see the r squared, we know r squared is x squared plus y squared equals 5 times, and notice we've got this r cosine theta. R cosine theta we saw in one of our conversions as well. That's equal to x. And so r equals 5 cosine theta is the same as the rectangular equation, x squared plus y squared equals 5x. Let's do one more. Let's do r minus r cosine theta equals 5. Well, right off the bat, I see r cosine theta. I know that's x. This one's going to take a little bit more work to make behave like we want it to behave. But how about we do this? Let's add r cosine theta to both sides. When I do, we get r equals 5 plus r cosine theta. Then what I want to do is let's go through and actually square both sides. When I do that, r squared on the left can become x squared plus y squared. On the right, let's leave the 5 plus r cosine theta squared. But this time we know r cosine theta is equal to x. And now we've changed it into an equation as a rectangular equation. Now we have something we are maybe more familiar with. So why do we do these polar form numbers? Well, you might notice that as we're making these conversions, we're starting with simple looking equations in polar coordinates. In polar coordinates, quite often equations look simple as polar coordinates. But in rectangular coordinates, they're much more complicated or complex. That's the advantage of polar, is we can work in polar, especially when circles are involved, to make graphing and understanding the function easier than in the less convenient rectangular form. We can also go the other way, though. We took these polar equations and made them rectangular. We can also take these equations and convert from rectangular to polar. For example, if I've got an equation like 5x plus 3y equals 7, this is going to be an easy conversion to make because we know what x and y are in polar. This is 5 times x, which is r cosine theta, plus 3 times y, which is r sine theta, equals 7. And technically, we could be done there. That's a polar equation now. But let's go ahead and solve these for the radius so that it looks kind of like a function, r equals stuff. Since both terms have an r, I can factor out the r to get 5 cosine theta plus 3 sine theta equals 7. Dividing both sides by what's in the parentheses, and the radius r is equal to 7 divided by 5 cosine theta plus 3 sine theta. And that's going to be my rectangular equation. Let's try just one more. What about x squared plus y squared equals 7? Now, before we just jump into using the strategy we just saw again, that would be using a sledgehammer to hit in a nail on this one, I think. We want to make sure we use the correct tool. Yes, I can replace x with r cosine theta, and I can replace y with r sine theta. Or I can notice that x squared plus y squared is one of our relationships to convert between rectangular and polar. X squared plus y squared is the radius squared. And so all I have to do is take the square root of both sides, and the radius is equal to plus or minus the square root of 7. And we have our function. Now, we've been talking about these functions in polar coordinates, how to convert between rectangular and polar, and we talked a little bit about how to graph points. But what's really interesting is if we take a look at graphing equations, because some of these polar graphs look quite interesting. And we're going to use, call this number 1. We're going to use our calculator to help us graph all the points. And as we do so, we need to make sure we're in the correct mode and convert it to polar mode. So if I want to graph r equals cosine of 5 theta, we can do so on the calculator. First thing I want to look for on the calculator is make sure I'm in the correct mode. If I click mode, we can see down here on the fourth one down is function. That's your regular rectangular functions. The next one is par for parametric. We're not doing that today. Next is polar. We're going to go down and select the polar coordinates. And when we highlight polar coordinates, now when you hit y equals, you'll notice instead of y equals, you get r equals. That's why we wanted to solve for r up above. So I can type in cosine of 5, and the same x we used before will now type in a theta, and I can close the parentheses. When I graph this, take a look at what we get. Looks really tiny. Probably should zoom in to get a better idea of what's going on. If you hit zoom and scroll down a bit, there will be a zoom fit option. And depending on the type of calculator you have, it might be a different number. It's number 0 on mine. But when I do zoom fit, that's going to zoom me in. One thing I notice about this graph is it looks really weird right now, kind of boxy. So let's go to the window and see if we can fix that. Here, I'm setting the parameters for what I want my graph to look like. Theta is probably the most important here. Let's take theta from 0 to 2 pi. That'll give us 1 full revolution of the unit circle. For the step, let's just put in 0.1. That should give us a small enough step that we get a good view of the graph. If it looks a little jagged, we can change it to 0.01, but let's try 0.1. And when I graph it, I'm still a little zoomed in. Let's go back to zoom fit again. There we go. Now we've backed up, and we can see what we end up with is this almost rose petal looking thing with 5 petals on it. That's kind of interesting. Let's try and graph another one. Let's graph the radius is equal to 2 divided by the square root of theta. We'll hit y equals, clear, 2 divided by the square root of our angle theta. Let's see what that looks like. Can't quite see that very well. Let's hit zoom fit again, see if that helps us. Well, that's an interesting curve. Bends around. I wonder if we gave theta more degrees to go around, if it would end up spiraling. Let's go back to window. And instead of saying x max is 2 pi, let's make x max 10 pi. So it's going to go around the unit circle 5 times. Yeah, look at this thing spiral in. That's pretty fascinating. And it looks like the spiral slows down. I'm guessing if we made pi even bigger, it would just keep spiraling in smaller and smaller. So if we did 12 pi or 20 pi or 100 pi, it would just keep spiraling in towards the center. Let's try and graph another equation. Let's graph r equals 4 sine of theta over 2. Let's see what that looks like. 4 sine of theta divided by 2. And let's just go ahead and hit zoom fit right now. It's calculating where to fit it best. Here we go. And that's kind of an interesting shape that we end up with, that polar graph. And because I said I was going to go till 10 pi, 2 pi probably would have been enough on this one. But because I said 10 pi, it's tracing it over and over again, making it real thick. So I can always adjust that by going to Window and say I just want to go 2 pi on the max for theta. And that'll probably just graph it one time. Oh, it only graphed half of it. So I can go down to 4 pi on the max. And that'll give me the other half. It's the first half and the second half. There we go. So take a look at playing with some of these graphs as you're solving equations between polar and rectangular. Go ahead and stick them in your calculator as polar equations. See what they look like. Some of these polar graphs are really gnarly. Make sure you're playing with adjusting the theta and how big you want to go to, whether it's 1 revolution of the circle or 2, or maybe you need to do more to get a full view of what's the graph doing. And take a look at these and play with them a bit. And we're going to look in our next video about how these polar coordinates can actually help us work with complex numbers in maybe an unexpected way. But for now, practice with polar, and let me know if you have any questions.